Hi everyone, this video is going to focus on section 6.3, finding probabilities for the normal distribution. For this video, you are going to definitely want to make sure that you have your note packet in front of you along with your TI-83 or TI-84 calculator, because we will be using that when we start diving into the practice problems. First, a quick history on the standard normal distribution and the z-score table, and I really do mean a very quick history. I just want you to note that we can use our calculators to determine the area under the normal curve for probabilities concerning a normal distribution. But back in the day, we needed to use a standard normal distribution table. And if you're curious as to what that looks like, feel free to Google it. If I am able to, I will also link it in our course. But just so you know, utilizing the calculator allows us to be a little bit more detailed where we are kind of restricted with the table. So moving right along, like I said, I told you it was a quick history. We're going to talk about the standard normal distribution. So the standard normal distribution has a population mean that is set equal to 0 and a population standard deviation that is equal to 1. And then again, this uses a value called a z-score. So to kind of add a little bit more context behind it, I'm going to go ahead and sketch in a normal curve. So again, your mean is set equal to 0. So I'm going to go ahead and denote it here. We know that the mean is going to be central in a symmetric distribution. And then in green, I'm going to go ahead and we're going to do 3 standard deviations above the mean and 3 standard deviations below the mean. So we use the standard deviation of 1 to indicate what the values underneath these green tick marks should be. So essentially, I'm just going to add 1 consecutively on the right side, and I'm going to subtract 1 consecutively on the left. So this is what a standard normal distribution looks like. So with regards to a z-score, say you are doing a calculation and you determine that you have a z-score that is 1.7. That means that your data value is 1.7 standard deviations above the mean. Above meaning to the right. So then anything on the left side of the mean would be below the mean. We would need to use the standard normal distribution when we work with the standard normal distribution table. Again, though, you don't necessarily have to convert everything into z-scores now because your TI-83 or TI-84 calculator allows you to kind of skip that step. You can just work with the information that's supplied to you in a given problem situation. And again, that'll be a little bit clearer as we progress through these slides. So now that I've mentioned a standard normal distribution and then I also brought up a z-score, there might be some lingering questions around what exactly is a z-score. So this is a standardized number that tells you how many standard deviations above or below a data value is from the mean. So again, just to reiterate, even though I know I just showed you, so forgive me for repeating myself. If we're looking at our mean on a standard normal distribution, which again, the mean is always equal to 0 in a standard normal distribution, anything to the right of our mean would be known to be above the mean. Anything to the left of the mean would be known to be below. So we'll go ahead and we will add that information to the two bullet points that we see below. So again, if your z-score is negative, it means your data is below the mean. And then I'm sure that you all can easily hazard a guess as to what the next bullet point will read. If your z-score is positive, it means your data is above the mean. And again, please feel free to reference the picture that I've drawn here. If you want to add this as well, you can note below means to the left. Above means to the right. Moving right along, the value of the z-score tells you the exact number of standard deviations a data value is away from the mean. And again, away referring to above or below the mean. Of course, we usually, when we are calculating our z-score, we will have to round. So we do lose some of that exactness because, as we had mentioned earlier in the quarter, whenever you're rounding a value, you are removing a little bit of that accuracy. But again, we don't necessarily want to present a z-score with like 9 digits after the decimal place. We usually round it, I would say, to the first or usually mostly the second decimal place, in case you're wondering. So feel free to note that down. As an example, a z-score of 2.5 means the data value is 2.5. Standard deviations above or to the right of the mean. And again, for those who want to add some visuals, how this might look, again, if we're talking about a standard normal, whenever we are dealing with a z-score, standard normal should pop into your brain, and that tells you that the mean is set at 0. And if we are talking about where to label this z-score of 2.5, I'm going to go 1 standard deviation, 2 standard deviations, we'll mark the third one, and then our z-score is going to live here, because that is where 2.5 is, specifically positive 2.5. So, still talking about z-scores. Now let's talk about the z-score formula. I've talked about this idea of calculating it, so I'm sure that there's a natural question that's kind of buzzing through your mind of like, okay, well, how do I calculate it? So the z-score formula for, let me kind of keep this organized, for a population, first is going to be where you take your data value, which we're going to label as x, and we're going to subtract that from our population mean. Remember that we use mu to denote the population mean. And we're going to divide this entire subtraction by our population standard deviation, sigma. So if it kind of helps, let's go ahead and label these. Just trying to find a different color to kind of keep it all differentiated. Okay, so remember that sigma is your standard deviation, mu is your mean, and x is your data value. So just as before, like earlier on in chapter 3, when we were talking about how to calculate the mean for a population and the mean for a sample, or excuse me, a mean for a sample. Shouldn't second guess myself, I did have it right. We use different notation, but essentially they were communicating the same process to you. Just on the outside, looking at the formula, they maybe look different because we used different notation to describe a situation where you're working with a population, and then, of course, your situation where you're describing a sample. So for your sample, oops, sorry, that was unintentional. Our formula is going to look like so. So we're going to start off with our data value again. That doesn't change. We're going to subtract it from our sample mean. And remember that our sample mean is going to be denoted with an x bar. And then again, we're going to take that entire subtraction and we're going to divide it by our sample standard deviation, which we use S to describe that. Okay. If it kind of helps, if you need to kind of keep your order of operations in control, if you want to throw some grouping symbols or some parentheses around that subtraction just to let you know, hey, do this step first when you're calculating for the z-score, feel free to include those. Now, as mentioned earlier in the video, I said that your calculator will be able to do most of this heavy lifting for you, where you're not always going to have to, for example, calculate the z-score and then reference a table of some sort, because you won't be provided a table in this class, admittedly. But the z-score can still be helpful to you. It can give you an indication if a value is considered extreme or unusual. So please remember that anything with a probability of 5% or less is considered unusual, and we're going to see this kind of pop up again later in chapter 6, 7, 8, and 9. I'm not going to go into too much detail about it now, but I would say feel free to like gold star this, because I think that it will, and I know that that's a purple star, this will come up later on. Also, why might it make sense that anything that is at or more than 2 standard deviations away from the mean could potentially be considered unusual? Think about your empirical rule here. So if you need to go back to your other notes about the empirical rule, or if you want to use the practice, pause the video for a moment and draw out what your empirical rule looks like with the bell curve. And actually, I'm going to go ahead and do that. So go ahead and pause your video, because the next time you click play, you'll see the image appear on the screen. Okay, now that we have the empirical rule kind of laid out for us, remember that the first 2 standard deviations contain a grand total of 95%. So that means that this tail over here is 2.5, this tail over here also has 2.5. So if you think about it, you're residing in the tails once you've gone past either of the 2 standard deviations, either above the mean or below the mean. So hopefully with this picture, it kind of makes sense that we are falling into these places where we have extreme or unusual values. Okay, let's talk about calculator notes. So you're going to need 4 pieces of information to use your TI calculator in order to calculate probabilities underneath the normal curve. And this is for any normal curve, not just the standard normal. So what will you need? You're going to need the mean. You're going to need the standard deviation. You are going to need the lower bound, or the limit, and an upper bound, or limit. Depending on the model of your calculator, an older version of the calculator is just going to take the normal CDF with an open parenthesis, and bring it to your home screen, where you are going to have to manually enter in the rest of this data in a very specific order. If you have a newer version of the TI-83 or TI-84 calculator, you're going to be taken to a second window where it's going to ask you to enter in lower bound, upper bound, mean, and standard deviation. For those of you who have the older version, like myself, again, if you click on option 2, it's going to take that normal CDF and it's going to basically carry it to your home screen. From there, you're going to want to enter in the value for your lower bound, then your upper bound, your mean, trying to be consistent here, and your standard deviation. Okay. Again, if this still feels a little bit murky because we aren't working with any concrete numbers, rest assured we will be looking at a couple of examples. So if you need to use infinity, so maybe your upper bound is infinity or your lower bound is negative infinity, it's going to be recommended that you use a value such as 1e99, which stands for the scientific notation of 1 times 10 raised to the 99th power. If this note fails you, for example, if you're taking a quiz or a test and you're like, oh, I know that I need to use like a 1E99, but I don't remember how to put that on my calculator, rest assured that what you can do instead is just type in a really big number to denote your upper bound, for example. So that would be 9999999. If you need to find a lower bound, then you would type in negative 9999999. So keep that as a backup, just in case. If you do want to end up using, say, for example, 1E99, you would first type 1 to represent this 1. Then you are going to hit second and the comma key. If you're wondering where the comma key is, it is located above the 7 key. So the E is going to represent your times 10. And then you would type the 99 to, of course, denote the 99. If you wanted to do negative 1E99, you would just type the negative key first. Remember that the negative key is located below the 3 on your keypad. It is not the same thing as the subtraction sign. If you use the subtraction sign, your calculator is going to get confused and go, I don't know what you want me to do, but I can't do it. So remember that you've got to do your negative, then you would type your 1, your second comma key to generate the E, and then you would type in 99. Okay, so example time. We're going to go pretty basic for now, but say we have the following situation. The amount of time for a student to complete a physical activity in a PE class is normally distributed. So that's kind of important to note. So when you hear normally distributed, you should think of your bell curve. Hopefully that kind of shows up. Let me do this in like, I don't know, like an orange or something so that we can see it a little bit better. There's your bell curve. That's standing out a little bit better. We know that it has a mean of 33.2 seconds and a standard deviation of 5.8 seconds. We want to round our answers to 4 decimal places. Now, while we practice, this is what I'm going to expect of you when it comes to assessments as well. I do expect you to utilize probability notation, and again, we'll talk about that. I want you to create at least one sketch of the normal distribution in the spaces below using the information that you know about the mean and the standard deviation provided for you in this situation. So we know that we have a mean, for example, of 33.2 seconds and a standard deviation of 5.8 seconds. Note if any of the probabilities you calculate would be considered unusual. For instance, would it be considered unusual for a student to complete the physical activity in 25 seconds or less? Again, I'm not answering that question, but just kind of showing you, like, this is the kind of question you should be asking yourself as we are working on these problems. Okay, so let's go ahead and move forward. I think for this problem, what I'm going to go ahead and do first is I'm going to do all the setups first, and then we'll jump to the calculator to do our practice. Hopefully that's okay. I know that you can't really tell me because this is a video and this is all coming to you from the past. So the first thing that we want to do is we want to state our random variable. Okay, remember that this is describing the variable that we are working with. So in this case, remember, we usually use X to denote this. And I would maybe say something along the lines of the number of seconds it takes a student to complete a physical activity in a PE class. It's really all the information that we have available to us, and it's really all that's been provided to us in the narrative. We don't, for example, know like the grade level or the age of these students or anything beyond that. So this is all we've got. Just make sure that you, for example, include the unit of measure. So we don't want to just say, for example, the amount of time it takes students to complete a physical task in a PE class, because is it being measured in seconds, minutes, hours? It would be a really long PE class, but you never know. So what I also want to do, and what I had kind of encouraged us to do, sorry, I didn't mean to make the screen warp, is to draw out your bell curve. It just has to be a rough sketch. It doesn't have to be anything super fancy. But remember that my mean in this case was at, I'm going to shrink my pencil thickness, 33.2. And actually, I think I'm going to try to move this up. Let me see if I can do that. There we go, so that we can just see those numbers a little bit better. And then I'm also going to include my standard deviation. So I'm going to go 3 standard deviations above the mean and then 3 standard deviations below the mean. So if I keep adding my standard deviation, which was 5.8, on the right, I don't want to erase, we should get 39, then 44.8, and then 50.6. Likewise, if we subtract 5.8 multiple times on the left, we'll get our 3 standard deviations below the mean. So that's 27.4, 21.6, and then 15.8. Okay. So the first thing that we're going to go ahead and do is we want to find the probability that a randomly chosen student completes the activity in less than 28.9 seconds. So let's go ahead and explore that. So I'm noticing it's saying less than. So what I'm going to go ahead and do is my probability notation is going to be the probability that my randomly selected student, their time is going to be less than 28.9 seconds. I don't need to include the unit of measure in my probability notation. So if I were entering this into my calculator, we know that we're going to use the normal CDF function. And here's where the shading might come in handy. So definitely follow along with this. So let's locate where 28.9 seconds would be located. And that's probably somewhere around here. It doesn't have to be super perfect, but I know that 28.9 is probably around here. And we're interested in the times that are that or smaller. So ask yourself, which side should you be shading? And hopefully you're saying, well, we would shade to the left. So we would have something like this. Okay. So in this situation, make sure that you have that cleared up or written down, because I'm about to clear it. So pause your video if you need to, but I am going to clear this so that I can keep using this bell shape for the next 2. So my shading, the lower bound, it went off to negative infinity. So I know I'm going to need to use 1E99 for my lower bound, and my shading stopped at 28.9. My mean, that doesn't change. That was given to us as 33.2 seconds. And my standard deviation was also given to us at 5.8 seconds. So again, we'll jump into the calculator after to look at this. I'm going to do the setup for part C and part D next. So for part C, we want to find the probability that a random chosen student completes the activity in more than 3.72 seconds. So this time our probability notation might look like P, or the probability that X, our random variable, is greater than 37.2 seconds. Again, our calculator entry, and what I would expect you to write down on your paper to indicate that this represents your work that you're about to do, we would now locate where 37.2 is, so it's probably like somewhere around here. Again, it doesn't have to be exact, it just has to be ballpark. And since we know it's more than, we're going to shade to the right, because that's where all the values are greater than 37.2 seconds. Again, if you need to, pause the video to get this sketch down, because I am going to erase it so that I can go back and utilize this same normal curve for part D. Okay, So in this instance, the lower bound, or in other words, where the shading started, was at 37.2 seconds. And then since we shaded off to the right, and there's no bound over there, it just keeps going on, we know that we're going off to positive infinity, so we would write that as 1e99. And then again, our mean doesn't change, nor does our standard deviation. Those were provided for us in the very beginning of the narrative. Lastly, we want to find the probability that a randomly chosen student completes the activity between 28.5 and 37.3 seconds. So 28.5 is somewhere here, and then 37.3 is somewhere here. So this time, our shading is going to happen somewhere in between these bounds. So our probability notation is going to be a compound inequality. Oop. There we go. So we are interested in the student that is between those two times. Again, we will defer to a normal CDF. And this time we can see that our lower bound starts at 28.5. Our upper bound stops at 37.3. And then again, our mean and our standard deviation remain the same. So we have all these pieces ready to go. Now we can go into our calculator and we can answer these. So I'm going to hop over there, make sure that you have your graphing calculator available so that you are able to follow along and do this with me. Okay, so we've made it over to our calculator, and we are now going to calculate the probabilities for parts B, C, and D in your note packet regarding the students and their times in seconds that it took them to complete an activity in PE. So for the first one, we had said that we wanted to find the probability that a random variable was less than 28.9 seconds. So in order to get to normal CDF, remember, you're going to want to press second and then vars, and that's going to open up your distribution window. And you should see that option 2, normal CDF, this is what you want to work with. So again, you can either arrow down to 2 and then press enter, or you could have just pressed 2 on your keypad. Either way, it will open up the window that you're looking for. So when I press enter, the calculator that I have on my laptop is a little bit more advanced, so it's taking me to a place for me to list everything. If you have an older version of the calculator, it's just going to carry the normal CDF function to your home screen. There will be an open parenthesis, and then you'll just want to enter the numbers for the lower bound, the upper bound, the mean, and the standard deviation in that order and separated by commas. So in our case, we said that our lower bound was negative infinity or negative 1e99. And again, they had it for some reason auto filled in here, but I'm going to go ahead and clear this out, and I'll enter it in with you all. So here we would want to hit negative. Remember that the negative key is at the very bottom underneath the 3. Then I'll press 1, then second, and then the comma key, which is located right above the 7. And then we will do 9, 9. For those of you, again, with the older calculator, you would press the comma key next to separate it from the lower bound and the upper bound. For those with the newer calculator, we'll press down and go and enter it in the upper bound. So 28.9. Again, older versions of the calculator, you'll press a comma to now enter in the mean. Newer calculators, we will arrow down. Our mean is a 33.2 seconds. Again, we'll go down, and then we will enter in our standard deviation, which is 5.8. We'll now, for those of you who have the newer version, you're going to want to arrow down and click paste. So highlight, paste, and hit enter. And then again, for those of you with the older calculator, this is what yours should look like. After your normal CDF entry, you should have your lower bound, your upper bound, your mean, and your standard deviation separated by commas. After this, we'll press enter, and here we have our probability. The probability is going to be presented to you as a decimal. So in this case, I would say we would round that to the fourth decimal place. So we should get around 0.2292, or in other words, there is a 22.92% chance that we have a student who has completed the activity in 28.9 seconds or less. Now, we can go through that whole process again for part C. And just for the sake of muscle memory or developing that muscle memory, let's go ahead and do that. So this time we want to find the probability that our random variable is greater than 37.2%. So I'm going to go to second vars for my distribution, arrow down to normal CDF, or press 2 on your keypad. It's a force of habit that for me to arrow down. Click enter, and this time my lower bound is 37.2. So notice I didn't have to clear it out. I could just start typing, and it just automatically made way for the new value. Likewise, this time I want an upper bound of positive infinity, so I'm going to press 1, second, comma for the E, 9. Sorry, that was really a high-pitched E when I was describing that to you. And then I don't need to change my mean or my standard deviation in this case because I'm still in the same situation as before. The mean and the standard deviation won't change. I can paste this in. Everything still looks good. I didn't have a typo anywhere. And I'm going to hit enter. And again, in this situation, we would, again, round this to the fourth decimal place. So this should be 0.2452, or in other words, there is a 24.52% chance that a randomly selected student is going to complete the activity. Okay, so now let's finish part D. If you don't want to go through that same process, the nice thing is whatever you had previously entered, you can actually have your calculator call back for you. So if you press second and enter, it brings all this information back. So it brings the normal CDF function, but now you can go through and you can just update the lower bound and the upper bound. So for part D, our lower bound was 28.5. And then our upper bound was 37.7 seconds. Or no, sorry, 37.3 seconds. My mistake. So I do have a little bit. Oh, no, I don't have a little bit. I was able to overwrite everything perfectly. So I can go ahead and click enter. And now I see that my probability comes out to, if I round to the fourth decimal place and convert this into its percentage form, 55.13%. So there's a 55.13% chance that I will get a randomly selected student that falls between the two times of 28.5 and 37.3 seconds. And if we kind of go back and look at our bell curve, that makes sense. We're mostly in the peak of our normal distribution, which is where most of the area under the curve is going to be located. Okay, so we're going to hop back into our guided notes. I will see you there, or I guess just keep watching the video and then I'll make my way back over to my slides. All right, so no, we can also go in reverse, meaning I can provide you the probability and you can find the corresponding boundary or data value. So again, I can give you the probability and you can find the corresponding boundary or data value. So we have a different approach when working with the calculator if we are going essentially in reverse. So again, you're given the probability value and you need to determine the data value. So we're going to need 3 pieces of information. For older calculators, you need the area to the left of your boundary in the normal distribution. So again, having a sketch of the normal distribution will help you determine what that area is. For newer calculators, you actually are going to be able to tell your calculator, I'm looking at the area to the left, to the right, or in the center of the distribution. Aside from needing to know the area, you again will need to know the mean and the standard deviation. Okay, so let's move on to the keystrokes. So in order to access this calculator function, which we are going to call inverse norm or INV-NORM, spelling it doesn't really make it sound any better, but here's what we're going to need to do. We're going to first press second and the vars key. So as before, you're going to have two different keys that you're pressing here. From there, you're going to be taken to your distribution menu, and here you're going to select inverse norm. You'll press enter. Again, this is what we will see on the older calculator, that it will bring that to your home screen, and that's where you're going to want to enter your 3 pieces of information. So once we have the inverse norm on our screen, we're going to enter that area to the left of our boundary. And specifically, what I want to call out here is enter this as a decimal. So if you are given the area as a percentage, make sure that you convert it. After that, we're going to separate the next value with a comma. So we're going to enter the mean after that comma, then another comma, and then standard deviation. Again, if you have a newer version of the calculator, it should provide everything to you as a list form to enter in first, and then it will paste the entire entry into your home screen before you have it calculate. So let's go ahead and take a look at some example problems. We're going to work with the same situation of the students in the PE class. So we've got 2 questions. One of them is 70% of all students finish the activity in less than how many seconds? And then 22% of all students finish the activity in less than how many seconds? So take a moment and again recreate that normal curve that we had created for parts A through D. So I'm going to go ahead and pause the video. I'm going to go ahead and pop them up onto the screen. Okay, so I have the normal curve sketch represented twice, one for each of the problems, so this way you don't have to erase anything. So for the first one, we want to know 70% of all students finish the activity in less than how many seconds? So in this instance, we're interested in the bottom 70%. So we know that like 50% is here right in the middle, so we don't have to have this be super accurate. This can be a little bit rough. So I would say 70% is maybe somewhere in here. So I'm going to go ahead and shade this just to indicate to me that this is the area under the curve where 70% is. Again, I'm shading 70% on the left side and not the top 70% because of how the question is presented. 70% of all students finish the activity in less than how many seconds? So all of our lower time values are, of course, to the left. So now if we were to kind of get ourselves set up, so just as before, I'm going to jot down what the calculator entry should look like, and then we're going to jump into the calculator and then actually do our calculation. So we know that we're going to do an inverse norm function. And again, the first piece, we want the area to the left of the boundary line. So this is our boundary line here. It's where our shading stops. So we are interested in the area under the curve to the left, which is going to be represented by 70%. You can type in 0.7 or 0.70. They do mean the same thing. And then we know from earlier our mean was 33.2 seconds and our standard deviation was 5.8 seconds. So again, we're going to go into our calculator and then we will calculate what this boundary line is. Before we do that, let's also talk about F. So here we've got 22% of all students finish the activity in more than. so many seconds. So the more than is kind of letting us know that our shading is actually going to appear on the right, because if we are shading to the right, our time values on our horizontal axis are increasing or going up. So in this instance, again, you don't have to be super precise here. I would say like maybe the 22% mark is somewhere in this area. And then again, we're also interested in all the other time values that are bigger than it. So again, this is representing your 22%. Again, if you're shading this and it turns out that your sketch is wildly incorrect from the solution that you get after doing your calculation, it's no big deal. You're just using these sketches just to give you a point of reference. So again, if you have an older version of the calculator, your calculator is only going to calculate the area to the left. So it's beneficial to kind of know, well, what is this area, this blank area? And again, we know that the entire area under the curve is 100%, and we're going to remove the 22%. So we now know that this area, the white blank area, is represented by 78%. So when you come to do your inverse norm calculator or calculation, we are going to represent the 78%. And again, the reason why I'm doing this is because for older versions of the calculator, it only lets you enter in the area to the left. That's what your calculator is going to interpret. You don't have an option to say, actually look to the right of this distribution. So we've got our 78%, and as before, our mean and our standard deviation, they don't change. They're still 33.2 and 5.8 seconds respectively. And again, these came from the narrative that we had at the very beginning of this problem. Okay, let's jump into our calculator and actually calculate these. So with this part, we're going to do our inverse norm calculations. So as before, we're going to go to second, vars, and as you can see, once we get into this distribution window, we can see that inverse norm is our third option. So as before, you can either bold the 3 and press enter to select it, or you can press 3 on your calculator. The newer version is going to give you all of these options. So in our first example, we said that the area that we were interested in was 70%, written as a decimal. Our mean was 33.2, and our standard deviation was 5.8. So this is the nicer feature on the newer calculator. It's asking you, is this shading, this area that you're indicating, on the left, the right, or in the center of your distribution? Older versions of the calculator, it automatically only defaults to left. So in this situation, I'm going to go ahead and keep it on left. I will paste this in. And again, this is what, with the exception of the word left, this is what an older version of the calculator should display. The area to the left, the mean, and then the standard deviation. Again, this left piece here is only for the newer versions of the TI-83 or 84. We press enter. We can see that the boundary line that we had picked, it should have been at 36 point, if we're rounding this to like the second decimal place, for example, 36.24 seconds. That's the boundary line that we would hit if we were shading. That would be our upper bound on our bell curve. So we can go ahead and do this again for part F. So second, vars. Again, we're going to go to inverse norm. I am going to only do everything to the left here, just to kind of keep everyone on the same page. If you want to calculate this on the right, if I've got time on this video, I will do that. But in this instance, we said that we were interested in the area to the left, which was 78%. I'm going to leave this as left, paste this in, and we're going to find out that that boundary line that we were interested in is going to fall around 37.68 seconds. For those of you who do have the newer calculator, let me show this to you really quick. If we go into second and vars, option 3, and say you entered in the 22% instead, you would need to make sure to select the option that says right, because that's where the area actually would have been. We're interested in the times that are greater than that. And again, this is a newer feature on the TI calculator. Not all of them have this option. So I'm going to paste this. And as you can see, we actually do get the same solution. This is only finding the boundary line. So this boundary line of roughly 37.68 seconds has an area of 78% to the left of it under the curve and an area of 22% to the right on the curve. I hope this helps. We're now going to move into a practice problem that I want you to try on your own and that we will check. Okay, so for the example that I want you to work on, let's assume that the price of the Microsoft stock is normally distributed with a mean price of $294.73 and a standard deviation of $25.77. So basically, I want you to run through similar questions that we had with regards to the PE example. So I want you to state the random variable, then find the probability that the Microsoft stock price is less than $260. In a different situation, find the probability that the Microsoft stock is more than $350. And then finally, find the probability that the Microsoft stock price is between $255 and $300. Go ahead and pause the video and work on just these four. Once you press play, we will go through those solutions. Okay, so we have our solutions here. Our random variable would be the price in US dollars, so we should mention the specific currency of the Microsoft stock. And then again, for B, C, and D, feel free to pause the video if you would like, but I've included the probability notation in blue for you, along with the normal CDF entry that you should have used in your calculator. So your lower bound is kind of noted in the green, then you've got that kind of lighter teal aqua color for your upper bound. For the navy color is your mean. Notice that that doesn't change. Likewise, the standard deviation is in the darker red. Again, it doesn't change because we are staying in the same stock situation. And then for each one, I included the full-blown decimal that you should have gotten from your calculator. I then rounded my decimal result to the 4th decimal place and then converted that into its percentage. That was just a choice on my part. Your directions didn't state for you to round in any particular place, hence the reason why I included all of the different stages of my answer so that you could see where everything aligns. Okay. So again, if you need to, take a moment to pause the video, go through those. If you have any questions, feel free to jot them down and either bring them to our DT or myself or another tutor. I'm going to take a look at the last two pieces of this question. So here, this is our going in reverse kinds of questions. I'm giving you the probability or the area under the curve, and I'm asking you to find where that boundary line is going to be. So we want to ask what Microsoft stock prices are 10% cheaper than the rest and what Microsoft stock prices are 20% more expensive than the rest. So if we were to kind of quickly do like really, really quick sketches of each of these, and by really quick, I'm saying like not even bothering to label the mean and the standard deviations here. If I'm kind of saying 10%, I'm interested in this area right here because I'm looking at the 10% cheaper than the rest. So all of our cheaper prices are going to happen on the left side of our number line. And likewise, if I'm interested in stock prices that are 20% more expensive, maybe they're kind of over here. And again, my shading is really, really quick. If you have the updated version of the calculator, you can say, okay, I'm interested in 20% to the right. But again, if you have an older version of the calculator, you have to enter in the area to the left of this boundary line. So this would be 80%. And again, remember that that is because the total area under the curve is 100%, and we're going to remove the 20% that we see over here on the right. So this is how we're getting the 80%. So again, go ahead and pause the video, play around with your calculator. When you press play again, I will showcase the solutions for these. Okay, so for part E, I've listed out what our inverse norm entries should look like. Again, I'm doing everything with the area to the left of that boundary line that we noted in our sketch. So this is why I'm using 10% and then 80% for part E and part F respectively. Again, the means and the standard deviations between the two stay the exact same because they are working under the same situation with the Microsoft stock. So for part E, we should have gotten roughly about $261.70 if you round to the second decimal place. I chose to do that just to include the dollars and cents. This is the most accurate we can get around money. And then for part F, we've got $316.42. Okay, so this completes section 6.3. I understand it's a long video. Thank you for sticking with me, and if you have any questions, let me know.